Okay, so in this video, this is the second time I made the video. The first time the audio wasn't doing what I wanted, so you may have tried to watch it and it didn't work. But anyway, we're going to talk about the concepts from class and just kind of build that a little bit. So I'm looking right now at case B from your Desmos activity that you guys were looking at. And you guys did make a table. So you guys got there and you had table for case and you had blocks. And so for example, we had case 1 through 4. And then you also had blocks 1 through 4. And so if I plotted those at 1, 1, I'd have a point, and at 2, 2, I'd have a point, and at 3, 3, I'd have a point, and at 4, 4, I'd have a point. And so we have those 4 points. And then one of the things we asked you was, is it a function? And yes, every time you have a case number, it's going to exactly one answer. So case 3, how many blocks were there? There's no confusion. The answer is there's only 3 blocks. There's not 3 blocks one time for case 3 and 5 blocks a different time for case 3. So this is a function. All of these are going to be functions because the case numbers all go to one set number of blocks. Okay, so then we also asked you if it's linear. And somebody asked if my dots make a diagonal line, is it still linear? And the answer is yes. If we can trace our values, our points on the graph with a straight line, like a ruler, then we say that that is a linear function. So one description for linear that we're using is that when we plot the points that make up the pattern, they form a line. Okay. We can also tell if it's linear if both sides of my table are going up at a constant amount. Like these are each increasing by 1. And the left-hand side is also increasing by 1. And we're going to talk more about that over, this few minutes in this video as well as next class. And then the other thing we asked was, could you come up with an expression? So a lot of people came up, if you did come up with an expression, you maybe said like x plus 1, and you're thinking because you're adding 1 each time. But that doesn't actually work. It's really close, and it was a good guess because you are adding 1. But if we look at it, we want an expression that represents like the case number and the blocks. So for example, if we called the case x and we called the case y, what's a function we could use to show how x and y are related? Well, we could say x equals y. Or if you look at it from a function perspective, we put y equals and then maybe mx plus b, if you guys saw that last year, y equals x. So whatever the case number is, x, that's also the number of blocks, y. So if you plug in the case number 10, how many blocks are there going to be? There's going to be 10 blocks. And it doesn't really matter if you're looking at it as y equals x or x equals y. The boxed answer would be how to write it as a function. Here's the second one. Again, if I make a table for cases and blocks, we have case 1, 2, 3. Our blocks this time, in case 1 we have 5 blocks, in case 2 we have 3 blocks, and in case 3 we have 1 block. And again, if I plot those on a graph, okay, 1 comma 5, 2 comma 3, 3 comma 1, I can still match all those up with a line, which means that it's linear. Another way to see that it's linear is I can see the rate that it's going down by in my table. I'm subtracting 2 each time. Over here, I'm going up by 1 each time. And this goes back to, I think, maybe Ian said it in class when we looked at our equivalent fractions, that as long as I'm adding the same amount to each side, I'm okay. Like for the numerator, when we were trying to do 3/4 and turn that into 6/8, almost everybody multiplies by 2, but you could also add the same as a ratio. I could add 3 to the top, I could add 4 to the bottom, and that still works. I could do that again. Plus 3 gives me 9, plus 4 in the denominator gives me 12. 9/12 is also 75%. 6/8 is 75%. So the same thing works with our case and our blocks. So the blocks are going down by 2 every time the case goes up by 1. And again, if I was trying to say, okay, well, maybe x, not x plus 2, maybe you're thinking x minus 2. Like you're going down by 2 each time. The down by 2 is correct, but how we write that as a as a function or as an expression, that is not quite right. And we're going to talk about that in class today, so I don't want to go into that yet. The x minus 2, you're thinking about it really well. You're taking a number of blocks and you're subtracting 2. But that expression doesn't really work, and we're going to talk about that more in class. I don't want to do that on the video. Okay, a couple things I want you to see is this one is called domain versus range. So I'm going to read the blue words. The domain of a function is the input values, like our case numbers. So in my table, it's on the left. A lot of times we use x for a variable to represent the case numbers. So for this problem, my domain is going to be 1, 2, 3, and 4. Okay, because those are the case numbers, or 1, 2, 3 if we did the previous problem. Right? And let's say that for those case numbers, we had a number of blocks, 3, 5, 7, and 9. So my range is going to be the number of blocks. A lot of times we call that the y values or the output values. Okay? So the outputs, if I tell you the case, you tell me the number of blocks. Okay, that relationship, those y values, the outputs, in this case the number of boxes or the number of blocks, that's my range. So we're going to be using the words domain and range. I have this little notebook icon here because that's something good for you to put in your notes. And then the next one is continuous versus discrete. I'm actually going to start with the red. What we've been looking at is we've been looking at discrete functions. So that means that only integers could be used as your domain, like our case numbers. So our case numbers were 1. Then maybe we had case number 3, then maybe we had case number 5. And sure, I could do 2 and 4 as well, but I don't have case number 1.62. I really don't have case number 1.5. So a discrete function is using integers for your domain, okay, which is what we've been doing, case 1, 2, 3, 4. A continuous function, notice a continuous function actually has the line. Okay, the discrete function just had these separate points, not really a line drawn. A continuous function has the entire line because it means that all integers and decimals. So instead of just case number 1 and case number 2, you have all the decimals in between. 1.1, 1.2, 1.3, 1.4, etc. And so it's continuous. You can think about time going by, right? So right now it's 8:32 or something, or it's 8:32 in 5 seconds. Now it's 8:32 in 6 seconds and 7 seconds and milliseconds in between. There's just, you can keep measuring that smaller and smaller and smaller and put that on a graph. And we're going to talk about what does it mean to be linear more in class today. But what we've shown so far with the blocks is that maybe it's going up or down by the same amount each time. Okay, up or down by the same amount each time. We call that constant rate. And you could say that the pattern, if you plot the pattern makes a line on a graph. All right, that's it.